get started. How's everyone? You doing good? Those sitting in the back, you can hear me? You can see the board? Okay. So I'm curious, any of you watching the videos? Not if you come to the class? Like within an hour, there will be like 20 views of those videos after I post. So who's watching them? You watching them? Okay. That's good. So makes Travis feel good that his work is appreciated, right? All right. Okay. So we will continue the drill on Simplex method through the example. So I put on the board what we had last time, it's a long example, right? So we had to cut it in half, cover half one class and half another class. Not optimal arrangement, but that's the best we can do. So we started with this problem. We want to minimize the z objective function, and these two are the constraints. And of course, everything shall be non-negative. So what we did last time, okay, so we took step 1 and step 2. So first we wanted to find a set of basic variables for the constraint such that after pivoting using them as basic variables, I will have a feasible basic solution. Is that right? So what we did, just trying to recall what we did, because this is a system with only 2 constraints, we have this graphical method. We checked the vectors of these coefficients. Is that right? All these vectors, we draw them, and we draw the vector on the right-hand side, and we try to understand that which 2 of them can be used to form a positive, non-negative linear combination to obtain the vector on the right-hand side. Is that right? And by that, we figured out, okay, one choice one can do was taking x2 and x3. Do we remember doing all that? I just want to try to give you the big picture today still. Okay, so now x2 is conveniently pivoted in this equation. And so for x3, we will pivot it in the first equation, right? And then you perform that, and then you can rewrite the constraint in the canonical form. And at the same time, you will also eliminate the basic variables in the objective function. Remember we did all that? So, okay, now these 2 are the basic variables, and the objective function is now expressed in terms of only the non-basic variables. So this will be a linear programming problem in canonical form. Is that right? So I'm saying that this will give me a feasible basic solution. So just to highlight that, how can we tell if the basic solution associated to this choice will be feasible? Just looking at these numbers in here, what will give that away? Any comments? What is the basic solution for the constraint here? I will set all the non-basic variables to be 0, and the basic variables will take the value on the, if these are all 0, what will the basic variable take value from? The right-hand side. Is that right? So the right-hand side here, they must be non-negative. Otherwise, the basic solution would not be feasible. Is that right? So just want to highlight all that, because later on all these will come into a big algorithm that we'll use. Okay, and then we looked at the objective function, and we realized that if a coefficient in front of one of the non-basic variable shall be negative, that means I could make this variable x5 bigger than 0, strictly bigger than 0, so that z will become even smaller. I can further optimize. Is that right? So the conclusion is now x5 should move into the set of the basic variables. to replace one of the existing one. And then we also went through an argument to figure out which one of these I should replace with. Remember? There's a lot of stuff going on. Okay, so we figured out actually that x3 shall be replaced. Is that right? So last time we did that. So okay, so this one, red light, because it's negative coefficient, that has meanings. Okay, so we pull that out, and then what we did, the conclusion in the end will be replace x3 with x5 as a basic variable. Okay, so now what will be my basic variable? So this leaves my basic variable choice with the x2 and x5. So I need to further pivot, right? So, okay. So all this is in step 3. Let's finish step 3. So in step 3, I figure out need to further pivot. I will be using x2 and x5. So x2 is already here. Everything's good. It's pivoted. And then this indicates x5 shall be pivoted in the first equation. Is that right? Are we comfortable with the process of pivoting? I think I label these equations as primes, right? Star prime. So these are the equations. We labeled them. Okay, so let's perform this. So our conclusion now will be pivot x5 in the first equation. Okay? So are we comfortable doing that? So what you can do? Well, we can take the first equation and replace it with the, I need to make the coefficient 1 in front of this variable. So I would take equation 1 and multiply by half and replace it, right? And the equation 2 shall be replaced by, I need to make this term disappear. So I need to take equation 1, multiply with, what should I multiply with to add on top of equation 2 to cancel x5? Wouldn't it be just the ratio between those two coefficients? And then take the opposite sign? Is that right? So negative 3 over 2, and then add on top of equation 2. Is that right? And then I also want to remove the basic variable in the expression of my objective function. So I want to cancel that term as well. Okay, so the equation star will also be replaced. So I see that these are conveniently of opposite sign, so I can just add it on top. Add 1 on top of equation star. Is that clear? This will give me what I want, right? Okay, so I will skip the details and give you the final form. So I have the following. Minimize z such that I'm not going to write. I'll just write out what I have. Negative 3 x1 plus half x3 x4 x5 equals to 3. Okay. Okay, so that's the new system we get. I removed the minimizing z, I didn't write all the non-negativity constraint, which is always there. Okay, so and we see that this has a basic solution, which we actually wrote out last time. We can be convinced. Looking at the canonical form of the constraint, I can just write it out. x1 is non-basic. x2 is basic, equals to 6. x3 is non-basic. x4 is non-basic, x5 is basic, I take the right-hand side, right? All the numbers you need to form that, they're all there. You just need to know where to find them, right? Or you put 0, okay? And then at the basic solution, what is the value of your objective function? Where do I find that? These are all 0. It will be the negative of that number. Is that right? Okay. So is that step okay? We all clear? All right. So now here comes the question again, as we were facing at the beginning of step 3. Now, is this the optimal already, or should I repeat whatever I did in step 3 to make it further better? Okay, so actually the next step here will be repeat the step 3, what we did there. We did not generalize the algorithm, but okay, as needed. Okay, we'll define that. Okay, so just looking at what we have now here intuitively, thinking what we did in step 3, looking at what we have here, do you think z equals to 15 is the minimal, or can it be further improved, get smaller? Any comments? So what gave away in step 3 when we figured out we could improve z further? Is this negative coefficient, is that right? And these positive coefficients, when we figured out that if we make them bigger, it doesn't help, is that right? So what about here? Do we have a negative coefficient? Yeah, we have one here. Here, this one. So we observe that we have negative x1 in the objective function. Okay, so negative coefficient. From step 3, from our experience, we know that x1 should be moved into the basic variable set. Okay, and then the next question will be, if x1 is a basic variable, then one of them, x2 and x5, shall be replaced, right? Which one? We need to figure that out, right? So which one from x2 and x5 shall be replaced? So how did we answer that question when we were in step 3? We figured out x5 shall be the basic variable, and we tried to figure out between x2 and x3 which one shall be replaced. Do you remember what we did there? So we are switching only one basic variable, right? The others will not be changed. So if we say x1 is going to be basic, it will switch one of them, x2 and x5. That means x3 and x4, they will remain non-basic. Is that right? And they shall be set to be 0 in the basic solution, right? So what one would do will be taking this constraint here, and in this constraint, I will use this information that x3 and x4, they are 0. I put that in, and I write it out again, and to see what it's telling me. Okay? So let's do that. So if I do that, I know that's 0, that's 0. So I'll have only x1, x5 in the first equation, x1, x2 in the second equation. So let me write out. So I have the following. Negative 3 x1 plus x5 equals to 3. 6 x1 plus x2 equals to 6. Is that right? Okay, and then I will express the old basic variable in terms of my candidate x1. Okay, so this will be 3 plus 3x1, and then x2 will be 6 minus 6x1. Because I wish to find out some constraint on how big this x1, the upper bound for the value, possible value for x1. Because I see if I make x1 big, negative x1 will be more negative, and it will reduce the z value further. Is that right? But you know x1 cannot be very large. There are some constraints here. So that's what we write out. And then we know that x2 and x5 shall be non-negative. That's the basic assumption for linear programming. Everything's non-negative here. So I have two constraints. Is that clear? This is actually later on, that's just part of the algorithm. We're just looking at it in a specific example. Okay? All right, so let's write out these two constraints. So here there's some situation. There's a situation that's new. We did not encounter actually in step 4. That is the first one. If I move the 3 to the right-hand side and divide both sides by 3, I have the following constraint. x1 shall be bigger than negative 3 over 3, which is negative 1. Is that clear? We can solve inequalities. And this one, I move this over. I'll have x1 less than 6 over 6, which is 1. Okay, which one is stricter? Will this ever need to be reinforced? x1 is a non-negative variable. Is that right? It's bigger than 0, so it's of course bigger than negative 1. So this one is always okay. Actually, it does not impose any further constraint. And this one actually gives me a constraint on how large x1 can be. So summing up these two, I see that the largest x1 I can choose here, which will give me the furthest reduction in z value, is when x is 1, x1 equals to 1. Okay, so let's push the limit. So I will take now x1 to be 1. That's my basic variable now. And if I let that be, and what will be my x5 and x2? I try to understand. So if x1 is 1, I put that in here. x5 is 6. And if I put x1 equals to 1, x2 is 0. Is that right? So we see that by setting x1 to be strictly positive, I make x2 become 0. So the non-basic variables are set to be 0 in the basic solution, right? So this is suggesting that this guy shall be replaced. This shall become a non-basic variable. Is that clear? So now your basic variable is the following. So basic variable would be x1 and x5. And you will move everything else to be non-basic. Okay? Can we write out the basic solution? Everything is actually already on the board before I do the pivoting. What will be the basic solution? So we are setting x1 to be 1. x2 is non-basic now, is 0. x3, x4 are both non-basic. They are 0. And x5 is 6. Is that right? I know that will be the basic solution. Okay. And what is the objective function? Z. What does z equal to at that point? Well, z equals to here, I can write it out again. Z would be 15 minus x1 plus x3 plus x4. At that basic solution, these two are 0, and that is 1. So I get 15 minus 1, 14. So you see that this becomes smaller after I switch my choice of basic variables. Is that clear? Okay? All right, so that is a decision you make at that step, that I will use these two as my basic variable, and you still have to finish the process by performing the pivoting, right? So let's do the pivoting. If you perform the pivoting process for this equation here, the constraint, so now I will keep x5 as a basic variable, so that's already pivoted in the first equation, and then I select x1 as the other basic variable, so that will be pivoted in the second equation. Is that clear? Is it okay I write out the end of this process? It's the same thing. Multiply this equation by 1/6, replace that, right? Multiply this with suitable coefficients and add on top of the first or the last to make this x1 disappear, right? Okay, so is it okay I give you the final form? All right? All right, so if you carry out this, well, it's just an algorithm. Probably a computer will work much better. If you write a correct code, it will always calculate and give you the correct answer, right? Not like me, if I do this, I always have to mess up these numbers. Okay, so let me write this out. x1 plus 1/6, x2. Now these are ugly fractions. x3 plus 3/2, x4 equals to 1. And then the last one, 1/6, x2, 3/4, 5, 2, x4 is -14 plus c. So this is the system that you have. Okay. Is it clear how we reached here? We basically repeated the step 3 one more time in step 4. Is that right? We did a similar thing. And now we reached, again, in the canonical form with x1 and x5 as the basic variable and with this objective function. Okay. So here's the next question. Should I repeat it again, or do you think I'm done? Do you think I've found the minimum? So here's the question. Let me put it on the top. Is this z equals to 14 the minimum? Or can it be further? Or could I switch? So the question would be, could I switch one and choose one of the non-basic variables and make it a basic one, switch with x1 or x5 so that the z will be even smaller at the basic solution, right? That's a long formulation of the same question. So what do you think? Shall we try to answer that? If I write out now the objective function, what do I have? Z, I move the 14 to the other side. I have 14 plus 1/6, x2, okay, 3/4, x2, 5/2, no, x3, sorry, 5/2, x4. That's my objective function, right? Write it again as z equals to something. But then we know we have the constraint for everything, all the variables that's involved there. They shall be non-negative. That's the region, feasible region, right? So we see if all these are non-negative, the smallest they can take will be 0. And then from this expression, we conclude that the objective function is bigger than or equal to 14. We agree? Because if we make any other change, if we make any of these to be the basic variable, to be bigger than 0, I will increase the z value. Do we see that? So there's no point in doing it, right? So let's put that down. If I shall increase any of these x2, x3, x4, to make it strictly positive, to make them basic, and then you see, because due to the fact that the coefficients here, all these three are positive, it will make the z increase, right? Z will increase. Okay, so why would I do that? So I will not do it. So don't do it. And further, by this argument, I actually know the smallest z can ever reach is 14. It cannot be even smaller, right? There's they can't go to negative. You cannot push z even smaller. Okay, so z reaches the minimum value, 14 here. Then the algorithm ends here. So you can stop the algorithm. We're done. Okay, so you can conclude, or your answer, conclusion for this problem, or the answer for it will be z reaches minimum value, which is 14, at the basic solution, one of the basic solution. So the one that we found there, that is 1, 0, 0, 0, and 6. So is it clear, this example? Was a very long example. I hope we remembered all the way we did along the way, even from last time. Any questions? Are we okay? Is it good? So this is actually a very favorable example that everything went very well. There are no complications. And we managed to find a minimum, which is a certain number bounded at one of the basic solutions. Okay, it doesn't always end that way, but okay, this is just to show you how this works. Okay, so let's summarize before we move on to talk about general theorem of this. Let's summarize from this example what we have learned. Okay. So we see that the main step of this simplex algorithm is this step 3, which we repeated again in step 4. And then if step 4 didn't reach the end, we actually would have to repeat it again, right? That is the algorithm. But the algorithm needs a starting point that is the step 1 and 2 that we did, okay? So that is our observation. So this simplex method begins with the problem shall be in the canonical form. Okay, this is actually implied that the corresponding basic solution should be feasible. Okay, and also the objective function is written in terms of the non-basic variables. Once we have that starting point, we can carry out this algorithm, step 3, basically. So what we did basically was moving from one basic solution to a nearby one, trying to minimize the z. until we reach the minimum. Is that right? In a short sentence, that's basically what we did. So we move from one feasible basic solution to another, okay, another actually nearby one in connected by changing just one variable, so it's a nearby one, to decrease z until reaching the minimum. So that's like just sentences and saying what we do, and then in the end we will we will design an algorithm and summarize everything in detail. Okay, so before we move on, I would like to give you a kind of a graphic interpretation of this algorithm, this procedure, what it is actually doing. Okay, so if I want to draw it in a graph, I have to restrict myself in a two-dimensional space, otherwise I can't draw it on the blackboard. Okay, so let's say the feasible region, I can represent it in a two-dimensional space as we talked about this earlier when we draw the feasible region for problem with two variables, and then you have it in a two-dimensional space. Because the constraints are always linear, we see that our feasible region will have boundary or straight lines. So it's a polygonal shaped region. Is that right? So let me generically draw a region to say that's my feasible region. So let's see. Okay, don't make it too complicated. Let's say that's my feasible region. Okay, so this thing inside here is the feasible region. It's just a graphic way of seeing what's happening here. Okay. And now your simplex algorithm, we notice that I have to find basically a feasible basic solution. It's feasible and it's basic. The basic solution will have all non-basic variables equal to 0, meaning the constraints will be all pushed to the limit. And what you will find will actually be all vertices on this boundary. That will be your basic solution, feasible one. Okay, let's say after step 1 and 2, I found one, so this is a starting point, okay, of my method. Okay, and then I try to move around, try to optimize according to the objective function, right? So let's draw the contour lines of the objective function, okay? So, okay, to make it easy, let's say they're horizontal. They're just parallel lines. I can rotate the graph so they're horizontal. So let's say these are the horizontal lines, contour lines of my objective function. Okay, so contour lines for z, okay, the objective function. And let's say if I move up, z increase. Okay, so z increases if I move from this contour line to the one above. So your goal will be, you will try to go down. Is that right? In the feasible region, you try to find the point as low as possible. So what is the simplex algorithm, at least the one that we did, what it was doing? Okay, it has a starting point, and then it wants to go to a neighboring corner vertex. If you switch only one basic variable in your set of basic variable, in principle what you're doing is you are just switching to one of the neighbor vertex corner. Okay, and then you check if I move to this one or I move to this one, would there be one of them that will make my z value smaller? Okay, so what will tell you? Well, this, where would that be? The negative coefficient in the front, that's an indicator, because you see, if I bring that one in, my z becomes smaller, right? So you would see, so here in this graph, you will see going to that point increases my z. I will not do that. Going to this point reduces my z. Then I will be moving here. Okay, that will be like step 2. Actually, that will be the result of our step 3 for what we did. We just, okay, that will be a second basic solution. And then you repeat. Once you're here, you search. If I move to this neighbor, will it be beneficial? If I move to that neighbor, will it be beneficial? And then you find out that, well, okay, this one reduces my z value, and you will move further down there. You always move along the edges of the boundary. Okay? And then once you are here, from the graph, it's clear you see that's the minimum, but if this is high dimension, you can't see, right? And the computer program will have to find ways of figuring this out. So if you are here, and then you check all neighbor points, meaning that you check if I switch any of these into my basic variable to see if z can be further decreased, and you find out that if I move here or move here, z will increase. All of my neighboring corners will actually make the z value increase. So you stop, you finish your algorithm here. So that's where the algorithm is being terminated. So you will stop here because you have reached the minimum. Is that okay? And that's basically it for the simplex method. Just that. But then, of course, it handles higher dimension problem. I cannot draw in this picture, but the idea is just like that. Is that okay? Right. Okay. All right. Let's get into some theoretical stuff. All right. I need more space. Okay, let's talk a bit in a general setting, and in the end, reach this algorithm. Okay. Did anyone look further into the textbook to see what's coming? Did anyone notice there is an applet offered by the author? You can go to their webpage and download, which will carry out this pivoting process. You know, the main calculation is this pivoting, is that right? And it can be easily implemented in an algorithm. Okay, so when time comes, I probably will give you clearer instruction of downloading it. But if you're curious, and go ahead and download and play with it. All right? It's a nice little applet. Okay. All right, let's talk a little bit about some theory. So, as we have seen in our summary, the algorithm starts from a canonical form. So we have to write that down, okay? So that's our assumption. And how to get there, we'll talk about that later. So assume that the linear programming problem here is in canonical form. Okay, so I will write that. And then M here, number of constraints, meaning number of equations. And then N here is number of variables. Okay? And let's say n is bigger than m. For most practical problem, n is bigger than m. That's okay. And then we have the following canonical form linear programming. Of course, minimize z with the following. So it's in canonical form. I will have a set of basic variables. I can always relabel them so that the first m variables are basic. Okay, I can always just relabel it. You can do that. So the first m will be basic, so x1, x2, they will be in a diagonal form until xm. These are the basic ones. And then the rest is non-basic. So let me write out the canonical form. So this will be plus a1. So this will be in column m plus 1 of xm plus 1 plus dot, 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 all the way to n equals to b1. Okay? And then x2, that will be a2 m plus 1 xm plus 1 a2 m xm. That's b2. And then you have many of these equations until you reach the last one, m plus 1 xm plus 1 plus a m. Let me write nicely. M xm b m. So these are the constraints, and then your objective function, which is only interpreted using the non-basic variables. So only these variables, and the coefficients are called c. So c, that's one coefficient, all the way to the last one, cn xn. That shall equal to z0 plus c. Okay. Okay, let me put the non-negativity here. That is always there. Okay? So in the end, is this part will keep changing as we apply the algorithm, right? Okay? And okay, so here all these AIs are coefficients. Okay, A, I, J, and B, I, C, J. All these are, and also the Z0. These are all just constants. They're given. Okay? You have all these. And furthermore, I want this to be LP in canonical form, meaning that the associated basic solution shall be feasible. Is that right? Where I set all the non-basic variable to be 0, my basic variable shall take non-negative values, which means the B here, all of these elements in this B vector on the right-hand side, they shall be non-negative. Is that clear? That's important, right? So is it okay I write further down? So everything will be here. So, and then also all the BIs for I from 1 to n, they shall be bigger than 0. Okay? So this will give you a feasible basic solution. So what will be the basic solution? Will we be able to write it out? Well, the basic solution will be x1, x2 will equal to just these b values, right? So xi will equal to bi for I less than m, and all the other x's will be 0. Is that right? Okay? Okay. So now, this here will be the starting point for the simplex algorithm. Okay? We know how to find such a feasible basic solution is a big deal, And we'll deal with that later, assuming we have it, and let's see what we can do. All right? So that's a starting point. So just want to say this is starting point of simplex. Okay? Like on that graph there. The first vertex corner I found already. And then I can start my searching for the minimum along the edges. Okay, let's take an example to reach to our first theorem. I think something that is already on your mind from the previous example we had, and we actually mentioned it a couple of times. But let's look at this example. First, to get ourselves familiar with the canonical form and all the things that's involved. Okay, so minimize z, where I have the following: x1 plus x3 minus 5x4. They're just numbers. Okay, and then of course non-negative. Okay, so first let me ask, can this be a good starting point for a simplex algorithm? Is this in canonical form? Would you be able to see that? This is the canonical form. What will be the basic variables? These two, right? x1 and x2 will be my basic variables. Is that right? So let's put a few observations. So in canonical form, already? So with basic variable x1, x2. So is it feasible? Can we find the basic solution? Can we write out the basic solution? Just pick numbers. They're all there, the numbers, right? What will the basic solution be? For x1, do we know where to find it? x1, you go to the right-hand side, take the b, is that right? x2, take the right-hand side. What about x3 and x4? They are non-basic. What do I put? Zeros. All right. And at the basic solution, what is my objective function? What is the z value? It's there. If it's in canonical form, it's there. You can just find the number and put it down. Where do I find it? When these two are all 0, is that right? What will z be? Negative of that one. Yeah. Is that clear where you find it? All right. Okay, and then the final question. Okay, let's say I ask you to solve this LP problem. And then you did this analysis, and now you're asking yourself, is z equal to negative 30 at that basic solution? Is that the minimal? Or should I carry out a step of the simplex? How do I know if this is a minimal or not? So. How do I find that out? Can I rewrite z equals to, if I express it out, 30 plus 2x3 plus 5x4. what gives away to see that this is the minimum? Do you think these actual number matters? If I put 10 here, will it change my conclusion? So what matters will be the sign. Is that right? These two are both positive coefficients. Meaning if I increase x3 and x4, meaning if I make one of them basic, I will reduce my z. Oh no, I will increase my z, which is not what I want. I want the z, sorry, negative 30 move to the other side. I didn't, negative signs are my enemy. They always mess up with me. Okay, looks nicer. So if I make x3 or x4, any one of them strictly positive, z will get bigger, and that's not what I wanted. Is that right? So from there, you see that z is bigger than equal to negative 30, and negative 30 is the minimum. Okay, so let me write down. So since 2x3 plus 5x4, the thing in the objective function, they both terms, they are with, what is important is positive coefficients. Okay, positive. So that means increase x3 or x4 will increase z. Okay, and you don't want to do that. And you say, I'm happy with this solution. So you conclude that that's the minimum, right? Z min is negative 30. That's as small as z can get. So I want to say that even though now this is given in a kind of a concrete example, you can easily generalize it, say these are just C3, C4 in an expression. All you need to check is the sign of all these C's, right? If they're all positive, non-negative, then you have reached the optimal point, the minimum. Is that clear? That gives you a criteria for you to check that you have found the minimum, that you can stop the algorithm. Okay, so we get that part first. When do we know I should stop my algorithm? Okay, so let's put this in the theorem. It's kind of important. I call this theorem O for optimality. Criterion. Okay, let's write this down using this form here, the general form. Okay, in I. Okay, so I will be just writing this observation for the problem in I. So for linear program problem in I, if I have these, all these Cj's are bigger than equal to 0 for j equal to n plus 1 to n, all the non-basic variables, then the minimal value of C is this negative C0, the negative of that constant. Is that right? That's where it reaches its minimum. And where is it attained? Well, it's attained at the basic solution. Okay, so how do I find the basic solution in the general form? Well, you see all the xi's as a basic variable should equal to the right-hand side. So I will have b1 for x1, b2 for x2, all the way to bm for xm, and for all the basic, non-basic variable x's, they will be all 0. Is that clear? Okay? So this theorem gives you a clear criteria to know if this is satisfied, then I stop the algorithm. I'm done. Is that okay? All right. So let me say stop the algorithm if all Cj's are bigger than 0. That becomes your simple criteria. Okay. Okay, then what if that criterion is not satisfied? Let's say that at least one of those C's are negative, like in the example we saw, right? And step 3, we took it because one of them is negative. Okay? So here's the next situation now. If, okay, let's say at least, okay, one of the Ci's is negative, strictly less than 0. Okay, let's give it an index. Say for index with k, ck is strictly less than 0. So I have ck xk, that term, with a negative coefficient. Okay? So if that is the case, what shall we do? What did we do in our example once we found a negative coefficient in the objective function? Okay, it's erased from the board, erased from my memory. So what did we do? We found one of them is negative. That means if I make xk strictly positive, the z value could be further reduced. Is that right? Because I'll have a ck times xk in the expression for z, which means I should bring xk into my basic variable. Is that right? That's what we did, right? Okay. So the conclusion for that, xk shall enter as a basic variable. That's a easy conclusion to make. And you want to replace it with one of the old basic variables. Then the big question is, which one do you replace, right? That is a harder question. So which one of all these x1 all the way to xm, that's the old basic variable set, to replace? That's a bigger question. Okay, so we need to figure that out. So remember in the example what we did. Okay, so let's say there is one row that's xk somewhere, ckxk. I'm going to make that into a basic variable, but I will only change one. So this one will be replacing one of them, and all the others are still non-basic. So at the basic solution, all the others will still be 0. Is that right? So what we did was we still set them to be 0 and write out the equation with xk and the previous basic variables and try to figure out what to do, right? So, okay, so what we will do, so in 1, is that 1? What we do, we will set all xj to be 0 for all the j's except the one, the xk one. I will keep that one. Okay, so which means actually you will see that now for each equation I just have two terms. One is this, for example, I will just have x1 and then the one including xk. Is that right? Each equation just two terms. So let me write this out. So we get the following: x1 plus a1k xk equals to b1, x2 plus a2k xk is b2, and I have a bunch of them, m a m k xk equals to b m. Is that okay? We did that, right, for the example. Now it's just general stuff. So what did we do? We need to figure out some constraint on the xk, how much we want xk to be big, but it will have some bounds. I cannot make it infinitely large because all these xi, x1, x2, xm, they shall be non-negative. Is that right? So what we did was we expressed all these in terms of xk. So this gives me x1 equals to b1 minus a1k xk, and all the way to xm equals to bm minus a mk xk. And then I know these are variables, they are non-negative. So actually I will have m different constraints, maybe different. In the end, I have m constraints or conditions for xk to satisfy. Is that right? So what we did basically was we wrote out all these and find out which one was the most strict one and do that. But okay, it's a bit more complicated here actually. We also saw in our example that some of the constraints come out to be always satisfied and some of them not. There are several different cases. Okay, let's do a discussion on that. We'll have a few cases. Actually, there are 3 cases depending on the coefficient a. Okay, so let's put up here. So 3 cases. Let's look at case 1. If I pick up the ith equation among here, and instead of xm, I have the ith equation, I pick out and I look at the coefficient aik, and I found that it's negative. What does that say? Okay, so if that is the case, so let's write out the ith equation. It's xi equals to bi minus aik xk, and it shall be bigger than 0. And then remember, this a is negative, so negative a is actually positive. Is that okay? So how do you solve this inequality? What condition do you get at the end? I could move the bi to the right-hand side, and then I have a positive coefficient. I divide both sides by it. Is that right? I keep the inequality. So this will give me xk shall be bigger than equal to negative bi. Okay, let me get rid of the negative sign. So it's bi over ai. Okay. Are we okay? We know how to solve inequalities. So pay attention here. bi is always positive, but aik here is negative, which means this number on the right-hand side here is a negative number. Okay. If bi is 0, it's 0, but okay, it's not positive for sure, right? Less than equal to 0. on that right-hand side. So does it give me any upper bound on xk? It says xk shall be bigger than equal to some possibly negative number, which is always okay because that's the xk has to be non-negative. Is that right? So this actually always okay. It doesn't give me any upper bound. Okay. Which means xk can be as large as possible. Because I want to make it large, because that reduces my z value. So if I do this operation now, if now I shall replace this xi with xk as a basic variable, of course, and then we will have the following. So the z would be written as negative z0 plus all the other non-basic ones. They will be 0. And I will have this term that is ck xk, which will enter. Now this becomes non-basic, right? So ck is negative. Xk can be as big as possible. And you want to drive z down, of course you would take xk as big as possible. You see that? So we see that as xk approaches infinity, it can just grow as big as you want, and z would go to negative infinity. So the minimum will be unbounded below. It can be as small as you want, as negative as you want. All right? Okay, if I don't find upper bound for xk, of course. So it's called unbounded below. Right, so that's one case. Now, the second case is actually very similar. Let's say this a, I, k actually exactly equals 0. Okay, so what equation do I have? So aik equal to 0, so that equation becomes xi will equal bi. Is that right? This term is 0. And I want this to be bigger than 0. It's always satisfied, isn't it? Because all the bi's are non-negative, right? So this is always okay. Again, so you can reach the same conclusion as case 1. Then I would take xk as large as possible and drive z to negative infinity, right? So you can conclude. So this is same as case 1, you will conclude. So here comes the interesting case. Say now I have a problem and I find a CI that's negative, and I looked at that column and I checked all those A coefficients, and I found out that they all fall into case 1 or case 2, meaning they're either 0 or negative. Then what can you conclude about the minimum for z? You want to comment? So, observation. If all of these, A, I, K, is less than or equal to 0, what happens to the minimum? Well, then you can just make this xk as large as you want and drive the z to negative infinity. Is that right? Do you see that? Z will go to negative infinity, and it will be unbounded from below. Okay, so let me state this as a theorem. Is the time almost up? Yeah. Okay, 5 minutes. Let's put it as a theorem. Let me put it back here. It's a bit important. So this is the second case where you can terminate your algorithm. You're done. So theorem, can I call it theorem U? Would that be okay? The other is theorem O for optimality criterion, and then the U is for unbounded minimum. Okay. Always the canonical form for that one. Okay? If I shall be in this situation, so the following. So if there is an index, let's call it K. K is between, so xk is a non-basic variable, okay? And it's in the objective function, so such that the ck in front of xk in the objective function is negative, then xk is a candidate for us to bringing into the basic variable. Is that right? Okay, and now once you find that out, and you're going to check the column of coefficients of those a's, and then you find out that that column, all the a's are less than equal to 0 for all I from 1 to n. Okay, then you are in this situation that we just made an observation from. So then you can conclude that the objective function is unbounded below. Okay? So usually the problem written in the form like I here, this shall be pretty easy for you to spot. So you would go through all these coefficients here and find a negative one, right? First of all, if they're all positive, you're done. You have reached the minimum. If one of them is negative, let's say this one is negative, then you look at the column of coefficients here, all these a's, to see if they're all less than or equal to 0. If they are, you can easily spot it, right? If that is the situation, then you conclude that z can go to negative infinity, is unbounded. And then you don't have to perform any more steps. Okay? You stop the algorithm here as well. So this is the second one that will make you stop the algorithm. Okay. Is that clear? So in these two situations, you can terminate. And then, of course, I say 3 cases, and there is the third case, right, which we'll talk about next time. I'll just write it out. So case 3 will be, I am not in this situation that all of these AIs are less than or equal to 0, meaning at least one of them is positive. One of these AIK is strictly positive. Okay, and we'll talk about that next time and figure out what to do there. Any questions? We're okay? All right.